It's our great pleasure. Now we are recorded. So it's our great pleasure to have Professor Leonardo Abbrescia of Georgia Tech and Vanderbilt to give the talk today. And he is going to join us. He's one of us, but he's going to come to Atlanta physically in the late spring. And he's going to talk about the structure of the maximum development in 3D compressible Euler flow, please.
Well, thank you. Thank you so much for the invitation. And might I start by saying it's a great honor to speak at this seminar. There's lots of really important talks being discussed, lots of very interesting mathematics being discussed at these seminars. So thank you for the invitation. Especially, in my opinion, shock waves are at a very interesting stage. So it's really exciting to talk about. So what I'm going to talk about today is joint work with Jared Speck, some aspects of it. And so let's get started with just a quick, where's my page number? Just a quick outline of my talk. What is the outline? So why can't I here? Okay. This talk concerns non-relativistic Euler equations. However, with vorticity being allowed, as well as entropy in 3 space dimensions, 1-time dimension. And there is, let me already say that there is a parallel work than what could hope to develop for the relativistic Euler equations, and that's something I'm working on, but though there are some issues, difficulties that I don't know if I'll get time to discuss. Okay, what else? So the regime that I'm going to talk about today concerns initially smooth shock-forming solutions. So the data at time equals 0 is initially smooth. So let me already say that this is different from the very influential work of Maida. Maida's very famous work on shock propagation. He put discontinuities on the data for the Euler equations, and he solved in a little neighborhood of the jump. As per the Reinke-Hugela jump conditions. So this is different. We're starting with initially smooth data, although let me just say we learned a lot from Maida's very amazing work. So I'm going to talk about how my work can be used to perhaps one day tackle some big open problems in the field. So one is describe the maximal globally hyperbolic classical development. So this is a bit of a mouthful. So let me sort of break it down piece by piece. What does maximal mean? It means I'm looking for the largest set of points in space-time on which a solution solves the PDE classically. So that's what classical means. It means, point by point, point-wise, the solution is, the equation is satisfied. And what does globally hyperbolic mean? I can tell you the rigorous definition if you want. Well, these are wave equations, so there's an intrinsic Lorentzian metric associated to them, and I can tell you that I don't want to get into the detailed definition what globally hyperbolic means, but it means that causality is preserved in terms of finite speed of propagation with respect to the sound speed. Okay, so that's what globally hyperbolic means. And then I'm going to talk about how my work can also be used to solve the shock development problem. I'll talk more about the shock development problem later, but right now, just to plant a little seed in the audience's head, the shock development problem concerns initially smooth data. You follow the flow up until the first singularity, and then from the first singularity, you solve a fully nonlinear hyperbolic system where you track the jump as per the Reinke-Hugela jump condition. So this is, again, different from the thing Maida solved, because here you're starting with smooth initial data, whereas the shock propagation problem or the shock front problem that Maida solved had discontinuities at t equals 0. Okay, so let me start with something we all know and love, the lonely burgers equation. But already I want to share that you can learn a lot from the Burger's equations, especially about shocks. So the usual Burger's equation you might have seen, of course, doesn't have the 1, but for the context of fluids, there's a sound speed, and for my case, it's approximately 1. So this is really harmless for the context of Burgers, but it better approximates the things I want to consider. The data, which I denote psi with a ring, is this odd cubic thing. And I'll tell you about why I'm choosing this particular data in a second. And let me firstly denote this solution-dependent vector field that shows up on the left side of the equation as L. And so you just rewrite the Burger's equation, you're just saying that psi is constant along the integral curves of L. Okay, and in fact, that's how we solve the Burger's equation using the method of characteristics. That's how we teach our graduate students. So if you consider, space-time with t and x, if you consider an integral curve of this equation starting from z, then what is a shock? A shock is a singularity where the solution itself is bounded, but what happens is that the derivative along the integral curves of L blow up in finite time. So there is a specific TZ where Z parameterizes the initial spatial location of the characteristic. And if you solve the Burger's equation, aka you integrate along these integral curves, then a shock singularity is one where you have gradient blow up, but the solution is bounded. Okay, so that's what we teach our graduate students. And in fact, you can consider much more, not just a single shock point, but because as I wrote it like this, the times which on which the singularity formed, they are parameterized by the initial location. You can in fact construct a full curve of singular points. So you can construct a full curve, aka you just plug in the characteristics. This is literally the characteristics which we know how to solve. And at this set of points, given any z, the solution blows up in finite time. Okay, and I'll show you a picture in a second. And what's important about this curve, what I already want to touch upon, is the fact that this curve is completely determined by data for Burgers in one space dimension. So if you look at the curve on the right, you see that t sub z depends on the initial data, and psi ring is, of course, initial data. So the whole singular curve is determined by data. In fact, it's not evolutionarily determined. It is completely determined by initial conditions. Okay, so I want to already plant this seed because this is not going to happen in multiple space dimensions. Okay. So let me give you a picture of how the singular curve looks like. So here it is. Here we have sigma 0 times 0. This is my axis. X is increasing this way. And so what are these straight lines? These are the characteristics. So if this is, if you want x equals 0. And so the characteristics from the right in this sort of purple color, these are straight lines, which we know from Burgers. And they are collapsing. They have infinite density along this singular curve, which is a cusp, right, like this, okay? And in fact, the way that the characteristics collapse along the singular curve is extremely rich. And so they actually do not intersect on the singular curve, okay? So this is something that can be proven based on what I'm going to tell you later. But in fact, if you want to say that the mapping from the characteristics from here to here is 1-to-1. So that actually they do not intersect. However, the solution nevertheless has a gradient blow up here. So the singular curve is B. It's this sort of cusp. The characteristics from the left blow up on this piece of the cusp. Okay, and notice that there is a characteristic, a single characteristic, which intersects the slowest piece of the cusp. And I'm going to call this the crease at partial minus b. It's sort of in the context of multiple space dimensions, you will see that this in fact looks like a crease. But nevertheless, so let me just sort of tell you more details what I have. So if you ask any undergraduate student when you have a curve, what do? They take the derivative. And this is just a quick exercise for you, that the derivative of the curve with respect to z is proportional to L. And so as you can see, if you sort of zoom in to the characteristics, they are tangent to the singular curve. So that's exactly what we're seeing here, that the tangent line is proportional to L. That's what I just said. And so that's now I can explain one of the reasons why I had this cubic data. Psi ring was a minus x plus 1/3 x cubed. Why one of the reasons I chose this data is, first of all, this tangency is not clear. Obviously, I didn't show you the details on what this coefficient is, but from this choice of data, this tangency is non-trivial. And moreover, one of the points of having this sort of data is that there is a distinguished first singular point, aka the crease exists and it is a single point due to this choice of data. So this is very different from the picture that you might have seen where the characteristics all intersect and collapse at one point. Here, the characteristics at the first singular point it's only blowing up again along a single characteristic. So that's something very different. Okay. So this is the picture for burgers that you can, that pretty much is just an easy PDE exercise for students. Now, what I want to tell you is that shock singularities, as per what I just showed you, in the sense of the singular curve, the place of the space-time points where gradient shows up, it is a culprit in the lack of classical uniqueness for the Burger's equation as a PDE. So what do we say? What well-posedness when we ask for a PDE is existence, uniqueness, and dependence on initial conditions being continuous. So actually, shock singularities, in fact, for Burgers, break uniqueness. So let me show you a proof, in fact, of this. So here, what I have done, this is a development of the data in the sense that this is a region of space-time points, not, I can tell you what it is. And so I consider this sort of half trapezoid here. I artificially cut off the characteristics coming from the left of the origin. And the characteristics coming from the right of the origin, I allow them to blow up. So they can go all the way up to the singular curve and they can blow up there. But the curves that were coming from the left, I'm going to artificially cut them off. Remember that these were going to blow up on this piece of the cusp. So these would have blown up over here in a cusp like this, but I'm not letting that happen. I am defining for you a set of space-time points where you can analyze the solution. Now, this is a classical development because take any point in this set of points. Let's say this point. Can you determine this uniquely by initial data? Yes, you can go back like this and integrate backwards along the integral curve. So in particular here, you can integrate back along this integral curve and get uniqueness of the data. Now, in terms of as a development. Now, here's another development. Now I'm going to artificially cut off the characteristics coming from the right, and I'm going to let the characteristics coming from the left blow up as they would normally. Okay, so these characteristics from the left, they blow up on the singular piece of the cusp, which is on the right, and these that would have blown up on this piece of the cusp up here, I am not letting them do that because I'm artificially defining this region of space-time as one where I have cut it off. And then I ask you, in this space-time region, can I determine the solution with the data? Yes, you can. You can just integrate back along every single characteristic. Okay. Now these are this is one development in the sense I just told you. This is another development in the sense that I just told you. And in fact, this is rather troublesome because they intersect non-trivially. And so this is a proof of lack of uniqueness for Burgers because from the same initial data, you have now a region of space-time over here where you cannot determine the solution in a unique way from t equals 0. Okay, so in this region of space-time up here, one of the solutions was blowing up here and the other was not, and vice versa over here. Okay, so these two solutions that I have constructed, these developments that I have constructed, they disagree on this intersection. And this, what is the source of this lack of uniqueness for as a classical PDE? It's the shock. Okay, so this is something that I really already want to show you for burgers. Okay, and okay, so let me stick to burgers for a little while longer, and so this is something that's known very well to the experts, but perhaps not to the rest of the wider PDE community. But in fact, the singularity for burgers can be renormalized away. So let me tell you what I mean. Let me define here an iconal function. So this is a solution to this sort of PDE. So this tells you that the iconal function is constant along the characteristics, whatever those characteristics were. This is this function whose levels, whose value along these lines are dictated at x equals at minus x. Okay, so that's what this PD is saying. Now, I'm going to define a dynamical coordinate system by this u. So I'm going to consider coordinates t and u. And I'm going to analyze Berger within these coordinates. And my claim for you is that these coordinates renormalize the singularity away. And there is some very interesting mathematics that you can do to get back the original singularity. So first of all, what is this vector field L with respect to these coordinates? It's nothing more than d by dt. In fact, I can prove this for you. You write this as alpha d by dt plus beta d by dt, du, sorry. Then what is beta? Beta is 0 because of this. And what is alpha? Alpha was 1 because, well, what was L? L was dt plus 1 plus psi dx. So LT was equal to 1. And that proves that L is equal to d by dt in these coordinates. Okay. So now let's see what Berger's looks like with respect to these coordinates. Remember, Berger's was just nothing more than psi being constant along the integral curves of L. So Berger's just is a transport equation that is completely trivial. So in fact, you can solve it with respect to these coordinate systems. The solution has no singularity. In fact, if your data is smooth, the solution is smooth forever. If it's analytic, it's analytic. If it's it is in fact smooth. So you do not see the singularity with respect to these coordinate systems. Okay. So where is the singularity? We already know that a singularity is there. So how can you recover the singularity from this from these coordinate systems? Excuse me. And that comes from something called the inverse foliation density. So what is it? It's very easy to define. It's literally just the Jacobian matrix of the change of variables between t and u and t and x. Okay, very easy to define. Now, we saw that the singular points, the set of singular points where the gradient blows up, there's infinite density of the characteristics. Okay, so if the characteristics, if u is constant on them, morally, you can expect that the derivative of u is blowing up. And so an infinite density of the characteristics corresponds to this denominator being 0. Sorry, this denominator being infinite. And so mu is equal to 0 whenever the characteristics have infinite density. Okay. And so the goal is to prove that mu becomes 0 in finite time. And that's how you recover the initial singularity. And my claim is that the cubic data that I gave you, remember minus u is equal to x. And so there's a minus sign here now. My claim is that this initial data forces mu to become 0 in finite time. And I can even give you the proof. It's fairly simple. So in order to control mu, you just derive the evolution equation for mu. So this is a calculation that d by dt of mu, what the transport equation satisfied by mu. This is an easy calculation, and I leave it to you as an exercise, it's not too hard, that this is equal to minus d by du of psi, the original unknown. But we know that psi is equal to its initial value. Remember, it was because d by dt of psi was equal to 0 in these coordinate systems. And so this is just the initial data. And from here, we have that mu, you can integrate this transport equation. So mu is just equal to this. And from this initial condition over here, you can in fact prove that mu being initially positive, aka the characteristics are spread out evenly, becomes 0 in finite time. And that corresponds to infinite density of the characteristics as per this formula up here. Okay, so this is how you get the infinite density of the characteristics. How do you see the singularity? How do you see the gradient blow up? That's just the change of variable. It's just a chain rule. So you rewrite the partial in x of psi with respect to d by du. Well, dxu is 1 over the foliation density. And d by du of psi is the data derivative because it's constant in that coordinate system. And so if mu is equal to 0, then the gradient blows up. So this is actually, you recover the original singularity using this procedure. Okay. Now, I ask you, now that we're all experts in PDEs here, if you have a function which is initially smooth and you have proven that it's going to 0, what is the generic thing that happens when you have a minimum, right? You have a non-degeneracy assumption at the minimum is equal to this, right? So this is the generic thing that one can expect to happen at a minimum for a positive function that becomes 0. And in fact, this I'm going to call transversal convexity for the remainder of the talk. And it's a very extremely useful assumption to have. And for this, this sort of, and in fact, based on this formula, you can consider, so you can ask the question, what sort of data give rise to transversal convexity or non-degenerate solutions at the vanishing of mu? You can actually prescribe it from data because mu is equal to a function of the data. So this is in one space dimension determined by the data. Okay. And so because I'm a firm believer that pictures say 1,000 words, so let me give you another picture of the same singular curve in the t and x coordinates. This is what we had before. And let me show you the picture in geometric coordinates. This is what it is. Remember, so mu was like 1 minus t psi prime. And what was psi? Psi was this cubic thing. So mu is a parabola, the level set. So this is why it looks like a parabola over here. The characteristics that were blowing up on this cusp on the right are now over here, and they don't intersect in these coordinates. And these coordinates, u is the actual coordinate. So these characteristics are just the vertical axes. Okay. But this is how it looks like. And I already want to point out that the singular curve, the cusp, in which is the parabola in these coordinate systems, the two connected components can be described or parameterized by the value or the sign of d by du of mu. So remember, transversal convexity says that d squared of mu du squared is positive, and so this thing is monotone, and you can prescribe a sign, or you can compute the sign of d by du of mu, and one of them is positive and one of them is negative. Okay, so I really wanted to take a lot of time of the talk to talk about burgers because it really gives context for what are the really important open problems in multiple space dimensions. Okay, so what do I want to do next? I want to show you that this uniqueness issue coming from shocks that was present in the Burgers equation is not present for Euler. Okay, so I'm going to give you a somewhat of a not really a proof. I'll just show you the picture of what happens. So if you have the Euler equations in one space dimension, for simplicity, assume that they are isentropic. So entropy is constant. Then it's a well-known exercise that the Euler equations, which I'll tell you the full system in a couple minutes, but they can decouple into essentially a right-moving Burgers and a left-moving Burgers. These are called the Riemann invariants, okay? And I don't even want to tell you the precise form of L and L bar, but you can think that L is like something like the right L for Burgers and L bar if you want to write the Burgers in the other direction, okay? The precise form is not important here, but what is important is now I can distinguish what we studied for Burgers that suffered uniqueness, which was the maximal development. What's different now is that now I can consider maximal globally hyperbolic developments. I can consider developments that obey causality, finite speed of propagation, domain of dependence issues that are associated to wave equations, okay? So, for the experts, you notice why do I keep saying wave equations? These are transport equations. It might look a little silly, but if you can believe, forgive me for a second to do something silly. If I take one derivative of L bar of the first equation, I write it like this, and of the second equation, I write it like this, minus and plus, and these are wave equations. Okay, these are wave equations in the t minus x and t plus x null coordinates u and v that we know from classical PDEs. And these equations over here are nothing more than the covariant wave operator of psi plus and m psi minus equal to 0, where the metric is equal to this. Okay, so that's what I keep saying, that there are waves associated to Euler, and in fact, the waves that are associated to this Lorentzian metric are those of the sound waves. Okay, I can talk more about that later if you wish. But why do I say that studying globally hyperbolic developments save uniqueness for you? And so I can show you the picture. The savior of uniqueness is something called the Cauchy horizon. So here is now the picture of the maximal development. Notice that the data that I had for the right Riemann invariant was the same data for Euler, for Burgers that suffered from uniqueness. It was the same data. But now what does the picture look like? The characteristics coming from the right are collapsing. They have infinite density on the piece of the cusp that was there for Burgers. But now what's happening is, remember what I told you about globally hyperbolic sets. Globally hyperbolic sets were sets where each point can be traced back to the data obeying causality, in the sense that I have to be able to integrate back between any point along characteristics into initial data. But now the point is I have two directions. So in here, I have to trace back, integrate back to data, and I notice I run into the singular point here. So in other words, you have to cut off the future domain of dependence of the initial singularity. And that's what the Cauchy horizon is. Excuse me. The Cauchy horizon is the domain of dependence of the initial singularity. So notice that these characteristics that were coming from the left, that were causing a lack of uniqueness due to them collapsing on this piece of the cusp, they're no longer doing that, because the domains that you're considering are not just classical maximal developments. They are globally hyperbolic. They have to obey causality. So the Cauchy horizon cuts off the development of these characteristics, which we are going to collapse over here. Excuse me. Okay, so that's the picture of Euler. So this is a picture that was well understood, maybe even by Riemann in the 1860s. But the main point of the talk today is that this picture is stable in 3 space dimensions without any symmetry assumptions. for small perturbations. So what I did with Jared Speck in 2022 was I proved that the singular curve, which in that paper I call the singular boundary, is stable. I'm going to tell you about all of the properties of the singular boundary over here. We have not finished, but are working very hard to finish the construction of the Cauchy horizon. There are more delicate issues that I can talk about later if we have time. But nevertheless, I want to emphasize what is the main difficulty. Why did it take, from 1860, the world of Riemann in 1D to all the way until 2022 to understand this picture? And the main difficulty is that the singular curve, which I wanted to plant that seed for you for burgers, which was determined by data completely in one dimension, is no longer the case in 3D. So this curve, you want to derive PDE estimates up to a curve that is not determined by data. So it's not given to you a priori. You have to construct it evolutionarily from the solution. So you have to derive PDE estimates on a curve that you don't know exists. And moreover, the estimates have to accommodate the singularity. So in all, this constitutes a fully nonlinear free boundary problem, which is extremely difficult to solve. So let me talk to you about this for the rest of the talk. But before, I want to just really paint clear the lessons that we should have learned in 1D. The main lesson is that we do not work with the t and x coordinates. We work with the coordinates that regularized the singularity, the t and u coordinates. Okay, and this is how the picture looks like here. And remember, this is the cusp that was blocked off by the Cauchy horizon. So in these coordinates, you can prove that the Cauchy horizon is actually cubic. And so that's why it cuts off those characteristics that were going to form a lack of uniqueness. Okay, so the lesson is you prove all of your PDE analysis, you prove all of your estimates in these coordinates, and then you have to control the change of variables map between t and u and t and x. Okay, and the other piece of the story is that transversal convexity, aka the convexity of this parabola, is completely fundamental for the problems that I'm talking about. Okay, the whole point is that if you consider, like I showed you very roughly, characteristics which are collapsing to a point like this, that sort of map from t and x is not injective. But if you consider characteristics which are like this and blowing up, like I told you, they did not intersect on the curve, this map is injective. And that's a consequence of transversal convexity. Okay, so these are the two main lessons I wanted to take a lot of time to talk about in 1D. Okay, are there any questions? Okay, so let me just tell you a little bit, not too much, because you can give a whole course on the theory of shockwaves in 1D. It's extremely rich. So for 1D, not just Euler, for a very general system of hyperbolic conservation laws, if your initial data is in a BV class, so it's a data that can accommodate jumps, then within the functional framework of BV, you can construct solutions, global solutions that are still bounded in BV, weak solutions, and the singularities are sort of incorporated, the jumps or the shocks, they are incorporated in the functional framework. Okay, so the theory of 1D hyperbolic conservation laws is much more well understood than 3D. Okay, so there's, of course, I really cannot do the field justice. I can just say that there's a lot of really, really influential people that have contributed to this world. Although I will say there's a very interesting result by Brisson in 2000, and he constructed large BV data and a hyperbolic system where the BV norm blew up. Okay, so even in one space dimension, there's still a lot of work to be done to understand things like this. Okay, and why is it so hard to go from 1D to 3D? Well, in excuse me, in 3D, you cannot sweep the singularities under the rug in the functional framework of BV. Okay, so there's a result by Rauch in '86 that said that for any multi-dimensional analog of BV that you can wish to construct, you can prove that the system, the quasi-linear wave equations are ill-posed in BV. And so really the only functional framework that is available for 3D wave equations are L2 Sobolev spaces. Okay, so having that in mind, what is the current state of the field? Because you cannot sweep under the rug the singularities in the functional framework, you have to describe the singularities and really give a full description of them and how they embed in space-time and regularity properties of the singularities that are not visible from the BV sort of framework. And I'll talk more about what I mean, more about a detailed study. That's sort of a very vague word, but I'll tell you in a second. Nevertheless, currently the most advanced results in the field still depend on the main idea which I presented to you, that you work in coordinates where the solution is smooth, T and U, relatively speaking. When I say smooth, that's a technical point you can ask me about. But really, there is a very important works by Valinak and Christodoulou, which I'll talk about later, that they were able to take the thing I just showed you for burgers and implement it for multidimensional wave equations. Oops, sorry. Okay, so that's that. And so in order to apply this framework, you have to understand the geometry of the singularities and rely on L2 based estimates, which are very difficult near the singularities. And I again want to sort of focus or bring your attention to the fact that currently the state of the field, the best results that we have are only for the transversally convex regime. So the non-degenerate regime, which I told you, where there is a single isolated first singular point in 1D, the stability of this regime is the only one that is still understood in 3D. So there's a ton of work to be done, and very little is known for other regimes that are not transversally convex. Okay, so let me now tell you now that you know all these words, maximal, globally, hyperbolic, and classical developments in 3D. So what do those singularities look like? So what our work does is we take 1D solutions with transversal convexity, and we add an initial perturbation at t equals 0 that breaks the symmetry, but does not break transversal convexity. And the word generic means it's an open set in some really large Sobolev space. Okay, so our work handles generic perturbations of transversal convexity. Our work reveals the full geometry of the singular surface, as well as the Cauchy horizon in 3D. And finally, our work reveals the behavior of vorticity and entropy along these surfaces. And I will sort of, the main PDE analysis I want to talk about later corresponds to new regularity theory that I had to develop with Jared Speck in order to accommodate vorticity and entropy along the singularities. Okay, so there's very delicate issues associated to regularity in the vorticity and entropy in 3 space dimensions. Okay, so this is really the main context of how our work sits within the broader field. And this is how the picture looks. So remember, the picture in 1D looked like this. Okay, so this crease, the singular point in 3 space dimension, is no longer a point, but it is a codimension 2 submanifold of space-time. Okay, the right piece of the cusp is now a codimension 1 submanifold of spacetime. I call this the singular boundary. So here I've drawn some characteristics for you, and they again have infinite density here, but just like before in one space dimension, the way they collapse is extremely rich. The geometry of their collapse along the singular boundary is very rich. Again, the map from the characteristics down here to up here is 1-to-1. So even though they have infinite density, the characteristics are never actually intersecting up here, which is very, there's a lot of really interesting things to think about there. Okay, then, like I mentioned, we were looking to study globally hyperbolic developments in order to avoid issues of uniqueness. And so you have to cut out from your space-time the future domain of influence of the singularity. So that is a piece like this, the Cauchy horizon. Okay. And again, I want to point out, what did the characteristics look like in 1D? The characteristics look like a curve, gamma t sub z, that was dependent on data. You can completely construct the characteristics and compute them from the initial data. In 3 space dimensions, the characteristics, you have to look at the wave equations that I wrote before and look at its symbol. And you'll see that in 3, the characteristics are given by a fully nonlinear hyperbolic PDE, which is called the iconal equation. And due to the Lorentzian metric, which governs the sound waves being solution dependent, these characteristics are not determined by data. You have to construct them along with the fluid. So it's a chicken and an egg problem. You want to control the fluid on the characteristics, but you cannot define the characteristics without control of the fluid. So all of this is done with a very complicated bootstrap argument where you control both things at once. Okay, so this is a huge pain in the butt. Okay, and so this is how the singularities look like in geometric coordinates. Again, you have transversal convexity in U. So here it's sort of hard to tell, but the singular boundary in these coordinate systems, this is the regular one. Remember, I took the cusp and then I flattened it out into a parabola. So that's this parabola over here. Now, the Cauchy horizon emanates from the crease, and it actually, like before, because the characteristics were straight lines in this coordinate system, they block the pieces that were going to develop the other piece of the parabola. Okay, so this is exactly like that picture in one space dimension where this piece of the parabola on the left was cut off by the Cauchy horizon. Okay, so this is the picture. And I want to stress that we have convexity again in U. So we have transversal convexity. This is the regime that we understand to this day. But I am not assuming any convexity of the perturbations in X2 and X3. Okay. That's something I want to talk about a little later. That's another regime that people have studied. All right. So are there any questions on the picture of the work? Okay. So before I tell you more about the PDE aspect, let me tell you why you should care about this result, because it's my result, so I'm very proud of it. But really, it sits within the broader framework of the theory, and really the use is to use my result to study 2 major open problems in the field. So what are they? They're the issue of uniqueness of the maximal globally hyperbolic development. So I'm going to talk about more about this in a second. And there's the issue of shock development, which we'll talk about also in a second. So here's the picture of the open problems. Let me tell you first. The first open problem, which is the issue of uniqueness. I told you that the Cauchy horizon prevents uniqueness from breaking because it prevents the characteristics to form the bottom piece of the cusp over here. So why am I telling you it's still an open problem? Well, my work doesn't tell you anything about the solution over here. And in fact, there's this very nice result by Eperon, Real, and Spiersky in 2019 that for very reasonable hyperbolic equations, you cannot prove uniqueness of the maximal globally hyperbolic development unless you know the whole thing and then prove that it satisfies a geometric property, that property being that it lies on one side of the boundary. So if you can take that result in good faith, this would prove uniqueness of the maximal development if I could prove that this goes all the way out to infinity. Okay, because then I would say that everything below it is the full maximal development and it lies below one side of the boundary. But I do not have that. So my result is a local result. It is a result in a neighborhood of the singularity. And so the full issue of uniqueness, where you have to construct the whole thing across all of space, is completely open. So that's something I'm working really hard on. Another major open problem, which I'm not working on, is the issue of shock development. What is shock development? If you consider the Euler equations in divergence form, if you wish, and consider the weak formulation where you do the usual thing by integrating on test functions, as soon as you see a singularity, the first initial crease of blow up of the solution, then you turn on the weak formulation and you posit one of the main axioms of a global theory of shocks is that there exists a curve in 1D or a surface in multiple space dimensions across which the solution experiences a jump and it satisfies the Reinke-Huguenot jump conditions. These Reinke-Huguenot jump conditions are needed in order to guarantee uniqueness. And this curve in 1D or this surface in 3 space dimensions, it emanates from the crease, okay? And this is another surface that you have to construct. It is not given to you. It is another fully nonlinear free boundary problem. And across this surface K is where the laws of thermodynamics tell you that the solution jumps, okay? Now, there's a bit of an issue here in the way that I drew it. You might say, hey, well, my solution is classical all the way up until the surface B, and the true shock development problem, the laws of thermodynamics tell you that there must be a jump in between K and B. And so, in fact, the classical solution and the weak solution that are predicted as per the laws of thermodynamics, they disagree. The classical solution disagrees with the physical solution between K and B. So why should you care about the classical solution if, in fact, the physical solution is the one that experiences the jumps as per the laws of thermodynamics? Why should you care about my surface B? Well, there is one and only one result in 3 space dimensions away from symmetry, and that's a monumental breakthrough in the field, where in Christodoulou in 2019 he solved the shock development problem. He solved the surface K. However, what he did is he did not solve it for the full Euler equations. He solved it for a system of equations that approximate the Euler equations in the sense that they do not see the jump, okay? And that's a little bit easier because you can show very well that across the jump, vorticity and entropy are generated. And so his result, in fact, is merely for irrotational solutions. And so why should you need my result? Well, the way Christodoulou constructed K is he did not construct the Cauchy horizon. He assumed the state of the fluid on the Cauchy horizon, and he used the singular surface B as a PDE barrier in his iteration argument. So he solved from the Cauchy horizon a matching problem to solve for the surface K, and he used the state of the fluid on B to make his iteration converge. Okay, so in the only regime of the shock development that we know how to solve, you need the full state of the solution on B. Okay, so that's what I want to say. I don't really, I'm running out of time. So I explained a lot of my solution, a lot of my work with the picture. So let me go to and pay homage to other very important works in the field. I mentioned that there is another regime that is studied. It's called the fully non-degenerate regime. And in this regime, transversal convexity is still present because that's the only thing that we can handle at this point in time. However, you also assume convexity in X2, X3, and 3D, or in X2. So you notice that the crease is a convex piece like this. So there is a isolated minimum of the crease. Whereas in my pictures, the crease is just an arbitrary perturbation of a straight line. Okay, so this is a different regime, slightly more restrictive, but this is a regime which was studied before us. So the first result of shocks in 3D rotational fluids was given to us by Alanak in '99, where he was able to follow the solution only up until the isolated point. So he assumes transversal convexity as well as non-degenerate convexity in X2 and X3. And he was able to follow the solution up until the first point. Okay. Then came Christodoulou, and he was able to describe morally a much larger piece of the singularity. So he was able to, he derived PDE estimates all the way up to B star in a very rigorous way. And then he told you that due to the convexity, well, you can take all of the slopes and the subdifferential of this convex set, and you can apply the same estimates on flat planes that you did here, and you can just tilt the planes to derive the same estimate over here. So in the way that Christodoulou wrote his book, you can get another piece of the convex singular boundary like this. There are some very delicate issues of regularity that I probably don't have any time to get into. But the first people to understand shocks in the presence of vorticity and entropy were Buckmaster, Scholar, Vico. So they assumed, again, a non-degenerate jump where it's an isolated first point. They were able to follow the solution up to B star. Also in 2020, Jonathan Luke and Jared Speck were able to follow the solution, not just up to B star, but they considered another regime where there could be other points over here that have a shock. But all of these results do not go up until the singular boundary or the crease. The reason I sort of jumped to this slide is because of a very interesting work that came out last year. So this is a result in 2D. So that's why I have X2 over here with vorticity. So there's a very interesting result by Steve Scholar and Vlad Vickel that came out last year. So they were able to give a complete description of the solution and the geometry of the singular boundary. So all of the surface B, as well as the Cauchy horizon. So they're actually the first people to construct the Cauchy horizon because, well, my paper's not out yet over here for this piece. But they were able to construct the solution up to the singularity. They again write the equations in a regular coordinate system, the T and U coordinate system, in a coordinate system related to that. They call it ALE coordinates. Their techniques for handling potential loss of regularity are brand new. So essentially, one of the things that there are two ways you can lose derivatives. One is by vorticity, and one is by the characteristics themselves also lose derivatives. The way that Jonathan Luke and Speck and Christodoulou handle the loss of derivatives for the characteristics is using the language of some techniques from general relativity. And Steve Scholar and Vlad Vickel, they came up and they found a brand new way to avoid a loss of derivatives of the characteristic geometry. So in fact, I think their work is really, really interesting because it can be potentially applied to other systems as well, where the Lorentzian nature of the general relativity techniques do not apply. Okay. So these are the other works that have been done in the context of shocks, and that's it. So I unfortunately don't have time to talk about the PDE analysis, but most of the PDE analysis is really related into getting these very sharp pictures. So let me talk about, future directions of the field in the last couple minutes that I have. Again, I told you that the issue of constructing a unique maximal globally hyperbolic development is open because you have to solve it across all of space and then apply the Éperon-Real-Spierski result. So this is open. I'm working really hard on this. The shock development problem in full generality is open. So Christodoulou was working on finished the shock development problem in the restricted sense where he considered irrotational fluids, but in full generality, it's open. I believe the last time I heard that he's working really hard on it, and it's an order of 3,000 or so pages. And a running joke is he's asking publishers if he can publish it on Bible paper because it's so many pages. So what else is open? Interaction problems. So one of the things I'm really interested in is if one Cauchy horizon intersects another one, or Cauchy horizon intersecting a singular boundary from another shock. So that's something I'm also interested in. The issue of global behavior of solutions with shocks is completely open. There's rumored to be a really interesting result coming out soon by Ginsberg and Rodniansky. There's also a very physically relevant and interesting world where you add viscosity into the system and you try to see in what way you can recover the shock as the viscosity goes to zero. And currently the best known result is by a very recent work of Chaturvedi and Graham, where they were able to control the shock pointwise all the way up to the shock in the vanishing viscosity limit. Before their work, I believe the best known results were in Lebesgue spaces. So they recover it in a pointwise sense. Like I mentioned before, it's an open problem to draw these same pictures for the relativistic Euler equation. That's something else I'm working on. I'm interested in it at least. And you can incorporate shocks with gravity. You can ask, do shocks exist in gravity? There are different types of singularities, and there's different types of wave phenomena when you add the effects of gravity. And there's rumored to be a very interesting result coming out from John Anderson and Jonathan Luke, improving shock formation for the Einstein-Euler system. And of course, you can consider other types of systems beyond this. For example, the equations of elasticity, crystal optics, and nonlinear electromagnetism. The equations for this types of systems, they look like this. So if you notice, the principal symbol is not a Lorentzian metric. There's 4 indices. And so whatever way you use to analyze the characteristics, it's not Lorentzian geometry anymore. So all of the techniques that I mentioned that Christodoulou used to study the characteristics using Lorentzian geometry and general relativity, they do not apply here, but perhaps the ones that Steve Scholar and Vlad Vickel are developing can. So I'm really excited about the state of the field. So again, this would require new geometry. Okay, thank you for your attention.
Okay, so let's thank Leo for this very nice talk. Are there any questions? Okay, so let's thank Leo again then.
Thank you. Thank you.